Hey everyone, great to be here. Really happy that everyone made it. My name is Tamas, I work at Intel, and Bálint works at Silent Signal. We're going to talk to you about case studies of fuzzing with Zen. Please don't sue us. The tool that we're going to be talking about is called KFX, and it's a mouthful. The project's name is, the full name is Kernel Fuzzer for Zen Project. That's what the marketing department approved. These days we just call it KFX. It's effectively a full VM snapshot fuzzer that's open source, and it integrates with AFL, AFL++. And in this talk, we will have, effectively it's two talks in one track. First, I will talk to you about fuzzing Linux Virtio, and then Bálint is going to talk to you about antivirus fuzzing using this tool. So I will talk first, and then Bálint will switch, and then my part is done. All right, let's get started. So in order to have a little bit of background of how this tool works, it's based on a hypervisor called Zen, and there is a feature in it that I implemented called VM forking that allows you to create a VM on the fly from a already running one and have it, the memory of it, be populated using copy on write. That effectively means that the fork VM starts up with no memory and you start mapping in memory as you need. So for example, for read and execute memory accesses, the pages are getting mapped in as shared, and only if a page gets written in the fork, that's when you deduplicate the page first, and that's when you actually put in the changes you want to. This means that you can create forks extremely fast, and it also means that you can reset these forks extremely fast. The only thing you need to do is throw away the pages that got dirty and reset the VCP registers. So this is obviously makes it a pretty solid base for fuzzing. The loop, the entire way of how this setup works with KFX is you boot up a regular VM on Zen called the parent VM, where you have your target code that you want to fuzz, and in the base setup, we recommend that you compile your code so that there is a magic CPU ID at the beginning of the code that you want to fuzz, and there is a magic CPU ID at the end of the code you want to fuzz, but you don't need a custom compiler. So any compiler works. It's not like AFL CC where you have to compile things to have instrumentation. We're going to be using the processor itself and the hypervisor for that. You run your code. The first magic CPU ID hits. The system knows that this is where the code starts, that you want to do your snapshot, where you want to start forking. You create a VM that we call the sync VM. And in this one, you actually locate in the memory of that where interesting functions are that you would want to be notified when the fuzzer actually hits those, such as the kernel panics, or you have things like address sanitizer, undefined behavior sanitizer. If those functions get called, that's due to some bug being detected. You want to save those. So we add a breakpoint into those locations, and those breakpoints will act as the crash that the AFL will record. From that, we create another VM called the fuzz VM. That's where the actual fuzzing loop, that's the VM that actually is going to execute. And here, the loop looks like you start the fuzzing, you read the input that AFL generates, you directly put it into the memory of the fork VM, and you hit run. You see what happens. If you get a breakpoint, that's a crash condition, right? Those are the breakpoints that we injected into the sync functions. So you report a crash back to AFL. AFL saves the input that reached that path, and then you can go investigate later what that input actually does to the code. If you catch the magic CPU at the end, you know that you reached the end of the code that you were interested in, so you can just go ahead, go to the next iteration. If neither of these happens, then you get a timeout. That's when you trigger the path in the code that somehow times out. It usually is a DOS situation. After that part is done, you can go and analyze the run. That's where the code coverage information that AFL needs is reported back. And that is done using the processor itself. So we are using Intel processor trace. Zen has a feature for it that can collect the execution log using the processor itself, which is extremely fast. And we decode that, and based on that, we report the coverage back to AFL so that it can actually fine-tune what direction it wants to mutate the input, what might be an interesting mutation to try next. Some of the design principles that I was trying to get into the system when I was building it is to have a stable foundation. I've been building hypervisor-based tools for close to a decade now, and the worst thing is when you are in the middle of trying to get something working and you have to worry about whether the hypervisor is not exactly doing what you wanted. So having a stable base where everything is upstream, where you don't have to custom patch stuff in and you don't know whether you did it right, don't have to worry about that. All of the features for this fuzzer are upstream in Zen. You have to compile Zen with expert features enabled, right? So this is not something that you would get by default, but it's upstream. You don't have to custom patch anything. Complexity, considering that this is a hypervisor-based fuzzer, is reduced because there is no ingest agent that you need to interact with. There's no synchronization with anything that runs in the guest beside that CPU ID, right? You just had one assembly instruction to your target code, and that's all that's needed. It's fairly flexible, so anything that's running within that VM should be fuzzable. And the components that we used to build this system are reusable and have a clearly defined role, and you can plug and play, and you can plug in any fuzzer you really want. So we just use the FL because that's pretty standard, but you can really use any type of source for the fuzzing. So there's actually a test case where we can just pipe in dev random into the VM's memory to see what happens. So you can use whatever fuzzer you want, really. Now, there are some limitations when you're fuzzing with these fork VMs, in that there is absolutely no I/O of any kind when the fork VM is running. That means that there is no disk, no network, no screen, no console, not even MMI or interrupts. That fork VM is literally running just with CPU and memory, so you have to take that into consideration, that the code that you are fuzzing is not something that is highly interactive. That's not possible to fuzz, because if it tries to reach out for an input, there's nothing going to be able to respond to it trying to reach out to an external party. It's not possible. But if you have a parser or some kernel code that's self-contained, and the input that you want to fuzz is something that it just received, you can totally do that. Now, bug enrichment features like address sanitizer, non-defined behavior sanitizer, that's absolutely something that would run in the guest, but it's compatible with KFX. So you can just locate where those handling functions are, and you can actually use these in-guest features to detect more bugs. And kind of an intuitive limitation is that, well, your target code kind of has to run within a Zen VM normally, right, in order to get to the setup stage. So the code needs to run normally in a Zen VM, which usually works okay, but there are some corner cases. One of those corner cases is VirtIO. The reason why we are looking at VirtIO is was part of a project for hardening the Linux kernel in preparation for TDX. There's a whole talk that Elena gave at the Linux Security Summit last fall. She goes into a lot more details. So what I'm going to talk to you about is just a small component of all of the work that we did there. But if you've never heard of TDX, this is an upcoming feature where the virtual machine is going to be encrypted. Only a few pages that will be used for I/O with VirtIO will be accessible to the host. So if you have seen any type of VirtIO fuzzing, that usually was guest to host. And now with TDX, that attacks, the threat model is changing, and we consider the host to be outside the threat boundary. So we want to fuzz and attack the VM from host to guest, right? So you will have only a select few pages that are accessible to the host to be used for implementing disk, network, console, and we want to fuzz those. So conceptually, you can think of these pages as DMA, but there is no IOMMU or anything like that. The host can read the other memory as well. Those are just going to be encrypted, but conceptually, it's like DMA. Now, Zen doesn't support VirtIO. Zen has been around longer than KVM. It has been around even before hardware virtualization existed. So Zen has its own implementation for implementing disk network stuff with shared memory, which is what VirtIO is as well. And the two are similar in concept, but the protocols are totally different, and Zen doesn't support VirtIO. So that kind of limitation that I just mentioned is means that, well, I can't set up VirtIO in a Zen VM because Zen doesn't understand it, so I can't get the kernel module into the state where it would need to be in order to fuzz it. So obviously, well, what can we do? We can't use this system for that. And I turned this project down a couple times, but then I started thinking that, well, maybe we can do something crazy. And I figured that the idea sounds kind of simple. Let's capture the system state on KVM, transfer it to Zen, load it up, and fuzz it, right? Well, sounds pretty straightforward, but it sounds a little wacky as well. So I reached out to some Zen developers as well to gauge what they think, and this is the response I got that, well, I don't see any showstoppers, but I foresee death by 1,000 paper cuts, which is always a good sign that this should be an easy task to accomplish. So, well, let's see how this goes. In order to capture the system state on KVM, we really have a reduced set of problems because we really only need to capture the memory and the CPU, right? That's the only thing we need for those fork VMs to actually execute. So we just need to find a way to dump that from KVM. There must be something. I've never really dealt with KVM too much in detail, but there must be something. You obviously can save a VM on KVM, so it must save these states somewhere. So just have to find it very exactly. There is this QMP command that you can send to the QEMU socket that intuitively called dump guest memory, which creates an ELF file with the memory content and the memory map. So perfect, that's exactly what we needed. And there's a surprise undocumented feature in this command that it actually saves the CPU register state as well in that ELF file in an ELF node that's not really documented anywhere. So I kind of stumbled upon it, but perfect. It has everything we need. It has the CPU and the memory. So this is awesome. This is up to a really good start. We still want to target the code specifically or where we want to take the snapshot, right? And for that, we need that CPU ID pausing that we used with KFX before that allows us to pause the system precisely. But that actually turned out to be not too painful either. On the top, you see the patch was like 5 lines to KVM to exit out when a magic CPU ID number is executing. And on the QEMU side, it's also like 6 lines to when that exit happens to just pause it. So perfect. This is, so far we are down to a really good start. And that only step we have left is loading the state up on Zen. Now this is where we would start to expect that death by 1,000 paper cuts. So let's start simple. Let's create a VM that's completely empty, no devices attached to it. This is the configuration file for it that you see up there. It just has memory, CPU, no devices, no VNC, nothing. But we add the VM trace buffer, that's the processor trace buffer that we can use to actually collect the coverage. And then we can just load the memory according to the memory map, that's easy. And then loading the register state was the only part that I ran into some issues in that the segment registers have different components. It has a segment base address, has a segment limit, and what's called the attribute bytes or attribute bits. And if you look at the format of it, it's all wacky and interleaved. And the way that they are saved is not standardized. So when QEMU saves it, the attribute bytes, it actually saves it in a 32-bit value, but those interleaved things like the segment limit and the base address are just maxed out, so those are 0. And Zen is expecting all that data in a packed structure. There's absolutely no documentation about that on the Zen side, so kind of had to figure out from, why is it not taking it. And, it was already starting to be pretty obscure, so all right, I got this one working, so let's try to get it working. And to the biggest surprise, it just works. So this was like, holy, all right, it's alive. What you see here is me creating that VM with that configuration file and loading with this tool called Zen Transplant. That's open source now. It's in the KFX repository. You pass in the data that was parsed out from that ELF file, the registers, the memory map, and the VM core is the actual content of the memory. It's loaded up according to the memory map. And then at the end, I just use Stepper, which is an MTF single stepping tool, and that code just starts running in the Zen VM seamlessly. That code is not aware that it got ripped out from KVM and now it's running on Zen. Has absolutely no knowledge of that, but it's just happily chugging along. So we are up to a really good start here. This just works. Now let's get back to Vertio. We have a way to save the state from KVM, load it up and run the fuzzer. Just have to figure out what to fuzz. Have you ever run into that problem? You have the tools, but well, what is it that you actually want to fuzz? Usually when we get a task of, hey, you should fuzz this, and you ask, yeah, but which part? You just get a hand wave like that. Whole thing. That usually is not very helpful when you actually need to put a harness around the code. So I don't know Vertio. I never really dug into it, and it was not really, my life plan to ever learn about Vertio. A you watched Mark's talk about people who will go to extreme length to not understand something, I'm that guy. I'd much rather do something that can do this automatically. And with VirtIO, it's kind of necessary because VirtIO will be used for, as I said, for all disk, all network, all console, and that's a lot of potential code paths that need to be considered as an attack surface. Who does even know how many different ways you can reach parts of the kernel that will start fetching stuff from disk or from network, right? You can make a guess, right? Anyone's guess. If you want to yell in some numbers, you're probably as good as anyone's guess. I have no idea. There might be 20, 30, 100, who knows? And if you have to do that by reviewing the kernel is kind of a massive beast, right? So if you need to read that and understand and actually figure out which part is worth fuzzing, you're gonna have a bad time, or at least I would certainly have a bad time, so let's not do that. We had kind of a similar challenge in a previous engagement, actually, when we were fuzzing XHCI, which is a USB 3 subsystem in the Linux kernel. Same thing, it's a pretty massive subsystem, and we kind of did a source code review that was painful, but we found some points that we could put a harness around, and we immediately found a bunch of bugs using KFX on it. And that was good, but we were always asked, like, did you consider all of the attack surfaces that subsystem has? And we said, well, we reviewed the code, that's what we found, but that was, the client was not happy about just, trusting us that we didn't miss something. So we built this tool called DMA Monitor, which can actually hook the DMA API of the guest kernel that's running within the VM, and actually remove the EPT permissions for the pages that are going to be used for DMA, so that when the guest is fetching data from pages that are accessible to the attacker, potential attacker, we can actually log the instruction pointer of what was the code that we saw that will actually fetch data, and that's the entry point to the kernel when it's receiving untrusted data. So those are the locations that we want to start reviewing the code and actually start potentially fuzzing from. Now, we could really use something like that for VirtIO as well, right? It's a very similar problem. We have no idea where the code is that we want to fuzz, and you can't really ask anyone because no one really knows. So we were in luck in that there is a project called KVM VMI that implements introspection for KVM. It's not upstream like on Zen, but it integrates with libVMI, which is what we use to build KFX and this tool called DMA Monitor as well. So we could lift all of this code onto KVM and arrive at a system like this. You boot your VM on KVM, and you enable the DMA debug API. We added a custom function there just to have all the information we need about when DMA pages are getting mapped in and unmapped from being used for DMA on VirtIO, so that we can hook it with the hypervisor and extract all the information we want, remove the EPT permissions from all the pages as they are being used for I/O with the host, and handle the EPT fault in the DMA Monitor tool. But we can do more than just look at the instruction pointer. What we can also do is we can unwind the stack at the point where that input is being read. And by unwinding the stack, we actually have a rich source of context under which that data is being fetched. So it's not just going to be the exact line in the VirtIO code base, which might be too low level, but we can actually discover all the possible stack calls that lead to data being fetched from an untrusted source. So that will actually have an answer to our questions of just how many ways can you reach that. Furthermore, using this stack as your context, you can actually just hash the stack return pointers, use that as a key in a hash table, and if it's a new context, you can take a snapshot automatically, which is pretty sweet. Here's a screenshot of how the tool works. On the right-hand side, you see the kernel booting, so it's just the virt manager screen. Everything is totally normal. On the left-hand side, you actually see that the EPT calls are happening. You see where the VirtIO PCI device is allocating memory for to be used with DMA. We remove the EPT permission, and then we have DMA accesses firing. We unwind the stack, and we calculate the stack key. And when it's new, we just dump everything into the files that can be then loaded up for Zen for fuzzing. The whole thing is automated. It's pretty sweet. Now, normally for fuzzing, you want to have the start harness and the end harness. Now here we have neither, right? Because we took the snapshot at the start of where the memory is being fetched, and we have no end harness. But it turns out we don't actually need any. We can actually look at the stack itself, right? We know where the code will go when it's finished processing the input, and we can just take that snapshot, dump it into a transplant, create a fork, and single step it up to a number of instructions that you'd consider fast enough for the fuzzer to be effective. So let's say 300,000 instructions. And then you just check the log of which one of the stack return pointers were actually hit. And you will put a breakpoint at the top one, because you know that that's the last stack return pointer the code would normally reach under normal execution. Well, that's your end harness right there. And with that, you have everything in place, and you can start fuzzing, and it's fully automated. It's pretty sweet. I never actually had to figure out what those kernel addresses mean, because actually loading up and fuzzing is cheap at this point. So the results we had for the 5.15 kernel, this is still with RC6, during a normal boot and normal execution, you get about 126,000 DMA accesses under various contexts. So there are 13 actual instruction pointers where data is being fetched. But the number of contexts under which data is being fetched is 738, right? So those are 738 different contexts that you would have to review by hand. And that's still a lot. And even for fuzzing, that's a lot. So we actually took 70 snapshots based on the top 5 stack frame uniqueness that will cover things like different system calls that lead to VirtIO, page fault, interrupts, background threads. There was an unbelievable number of different contexts that I never even thought were possible to reach VirtIO, but they did. So it's pretty cool. We fuzzed it for 2 weeks, all of these snapshots. We got 7.5 billion fuzzing cycles. And drum rolls, we found no issues. So that was kind of a bummer. What this means that there was no address sanitizer reached, no undefined behavior, no panic nodes, none of those functions actually were hit any of these fuzzing instances. But we found 13 snapshots where there were hangs, right? So the code would run into an infinite loop or something like that. Unfortunately, that's outside of the threat model with TDX, because the host is always in control of when a VM is getting scheduled. So a host could always just choose not to schedule something. So the host DOSing the VM is kind of not really an issue, so that's also a bummer. Interestingly, out of those 70 snapshots, 54 had very low path discovery, right? So that's the downside of doing this automatically, is that you will have a lot of overhead with fuzzing things that you might have not considered to fuzz if you did a code review. But on the other hand, CPU time is cheap, and if you can automate it, it's just the cost of doing business. So no bugs, right? That's the bummer. But it turns out that we were not the first one to actually fuzz these interfaces with the address sanitizers enabled. There's this paper that came out actually a couple months after we started this project where they actually fuzzed the 5.10 kernel and reported all the sanitizer bugs that were found on the VirtIO interfaces. So I figured, all right, well, they did this fuzzing on 5.10. Let's validate that this whole craziness actually works, and it's we didn't find any bugs, not because the system is broken. And we fired this up on 5.10, picked a random snapshot, and bugs just immediately start shaking out. So it's what we were originally expecting. So the system works. It's just these low-level bugs have already been fixed. But there are other sanitizers. There's other snapshots that can be taken in other contexts. So not everything is lost. So there might be many more bugs to be found there. And I still consider this whole thing a win because, first of all, they open sourced all of these. So you actually have tools now to target some of these interfaces that you couldn't before. The guys who wrote this paper never released their code. Now we have tools to actually do this. And furthermore, this ability to disconnect the setup of your target and where you need to fuzz it, I think it's pretty huge because we can actually snapshot systems on various setups. We can use QEMU, KVM, Symix, or really any system where you have access to the system state And you can take a snapshot of it, load it up on Zen for fuzzing, and you can achieve a lot with that. So that was my part of the talk. Thanks to a whole lot of people who made this possible. And now Bálint is going to switch gears and look at something that I never considered to be in scope for us, and that is fuzzing antivirus solutions. Bálint, thank you everyone.
So, hello everyone. I'm Bálint, moderator. Thanks Tamas for this great tool. He's the big brain behind it all. I just do a lot of testing. And one of my main ideas when this thing came out was, what if I could use this tool to my really weird Windows user space targets, namely antivirus. Of course, antivirus is a really nice set of targets because it's a widespread technology. It's installed all over the planet at all large companies. And in order to be able to find all the nasty malware hidden inside, I don't know, compressed archives or a PowerPoint presentation, for example, they need to implement really complex parsers, a lot of them, and they are usually done this in C and C++, so a chance for a memory corruption is pretty high. As previous research showed, this is, of course, a remotely reachable attack surface, and just to use a fashionable word, it also can be a zero-click, because these things run on, I don't know, gateways, and they can even trigger when your web browser caches some file to your disk that you didn't even want to download. So, but why don't we see that many attacks on antivirus software in the wild? Well, there's a possibility that we just don't see them. But of course, there are some difficulties. Antiviruses are complex software, similar to Office Suite, for example. You don't have any source code with it, so it's completely opaque. You don't have a public backtracker to look for nasty developers, and of course the performance is not the greatest virtue of this set of software. But these are things that that you get when you target, for example, Excel. What makes antivirus research especially frustrating is that these software are really not into being watched. So they implement all kinds of rootkitty, anti-debug techniques in order to avoid inspection, and this is just what we want to do when we are fuzzing in order to have some information about if we are going anywhere or not. They also handle quite a bit of state. For example, if you scan the same file twice, the second scan usually won't trigger the same code path because the hash of the file is already cached somewhere. We know it's not malicious, so you can just let it through. See performance above. And last but not least, and this was my the starting point of this quest for me, is diversity. So there is no such thing as an Excel of antivirus software. There are many vendors, many products of a single vendor, and of course these individual products can contain a lot of different parsers, so we need to automate this in order to have some nice coverage. This is where KFX comes into play, and cannot really agree more with the first keynote of the first day here. Is like yes, you have to understand your target, but if you have to create like super specialized harnesses for each of these targets, like Symantec, McAfee, ESET, blah blah blah, then you won't have time to understand the code. So there would, it would be nice if we had something that can guide our manual research and serve as a spotlight or a torch that can show us what are the most interesting parts are, or maybe. So with KFX, we first and foremost get a reusable harness. As you will see, it's really easy to adopt it from Linux to Windows, and inside the product to different parsers and to different products. This tool also provides us with full inspectability, so we don't really have to care about anti-debug bullshit. And we also have the full system state. This is also really important because antivirus tends to be comprised of many different components that are interacting with each other. And if if you can't set up the appropriate state, they will do nothing. And last but not least, there is documentation, there is code outside, and it takes like a couple of hours to set this up. It's not like you have to watch like a week of Twitch streams to build some really special hyper-based stuff, which is also pretty cool, but this one you can actually use immediately. So let's look at how we can turn our idle CPU cores into cache with Symantec endpoint protection without paying shitcoin to Broadcom. So a few words about this particular product. It, of course, implements what they call tamper protection. This is their anti-debug mechanism, but the vendor was nice enough to provide an option in the UI that you can just switch it off. So what's the big deal? The problem is that even with the tamper protection off, you can't really reach some pages inside the process memory and userland that we are interested in. So there is some kernel witchcraft probably, but I don't understand that part. Also, which took me a lot of pain, is that Symantec runs a system service called CCSVC host that works really like Windows' service host processes, but it also implements an architecture that is really similar to Windows' COM. So there is this separate registry structure for the elements of the software, and by UUIDs you can load up stuff from different DLLs by calling their get factory method and providing that UUID. But this means that you can't really just get a DLL, write some harness around it and call a method, because when you get the object from the factory, you have to pass other objects from other components, and if you don't know how that works, and it's not documented anywhere, you are out of luck. Also, there is OS interference, for example, because this product tries to catch malware on the network too. If you set a breakpoint somewhere in the process and it's hit, then you cannot communicate, for example, with Reddex, so you can compare your static and dynamic analysis results, which is quite frustrating too. So I wanted to do a proof of concept too, so I went to the Project Zero backtracker, where Tavis Ormandy in 2016 published a whole bunch of Symantec bugs. These mostly affected the so-called decomposers, which are the modules that are able to extract data from different container formats, so to say, like compressed archives, PowerPoint presentations, and whatnot. I choose this one with the ID 823, which is PowerPoint misaligned stream cache remote stack buffer overflow. It is a really nice assembly port that was easily modifiable, and the description of the bug also led me really easily to those parts which are vulnerable and those parts which accept input from the user from the disk. So these are basically the things that you need when you're using KFX. So I installed a Windows guest VM with Xen and tried to use KFX with it. The first problem that we noticed was that unlike Linux, Windows tend to use some timer interrupts to transfer control from time to time from user space to kernel land, and we don't really want to do that. That's why all interrupts are being masked. Otherwise, it was easy peasy. There is an H5 where you can set where you think the crash conditions are, and in Windows, the most obvious target for this is the kernel level exception dispatcher, which can be looked up by volatility, and you just place a breakpoint there, and if it ever hits, then you get a notification on your fuzzer. I also mask out any kernel addresses to not to be reported to AFL. This helps with stability. One drawback with this particular sample is that it was a quite large test case, but as we will see in the next demo, it could be circumvented. So here I am, just SSH'd to the Windows virtual machine. Installing OpenSSH on Windows took like 3 months, of course. Most hard part of the project. And we just attach our favorite debugger, in this case CDB, to look inside the system level process. As you can see, there are a bunch of DLLs, so there's real complexity here. You can basically forget all your CTF2s and whatever. And we set our first breakpoint at that function that we think is reading up data from the disk. We go to the VM and initiate a virus scan, and we can see that this breakpoint hits. Since the test case is quite large, we have to hit this breakpoint multiple times. Each time it will read up 8Ks from the file. But around the 6th or 7th time, we reach to the point where there is that particular attribute that will cause our crash. Now we set another breakpoint which allows us to inspect the actual read file operation. And the result of the read file operation will be stored in a local variable buffer, stored at EBP +8. As you can see, all 32-bit, because of legacy reasons, many antivirus are still 32 bits, which makes things easier, I think. So now we can see that, yeah, something was read from the file, but it's still not the buffer. But I know how the buffer looks like, so I will know that this will be the time. Oh, and important point, this file will not crash the target. So this is like a non-malicious file. I just know its contents. Yeah, this is the buffer content that I was expecting. So I write down this address. This is where we will inject our new inputs. After this, we set a breakpoint that will trigger the snapshot creation, and we also inspect the call stack in order to find a common ancestor of the file reader function and the target function that we want to crash. And we set a breakpoint when this common ancestor returns. So this will be the end of our fuzzing cycle. This will be the point when everything goes back to the beginning. This way we can not just fuzz a single function, but a function and its context. And we also place a bunch of breakpoints at like common operations that can trigger device access, like read file or load library. We don't really want to go to paths where these things happen, because everything must be in memory. So this is our final breakpoint list. And now we have to run KFX in so-called setup mode and just make the target reach the next breakpoint, so that will trigger the snapshot creation. Yeah, it happened, and with the actual fuzzing, we've used AFL and AFL++ more recently. We just have to tell KFX that it should inject to that address that we copied from the local variable, that points to the local variable. And with this, we'll see that in a short while, the path number will start to increase, so we are doing something. And eventually, this approach was good enough to find the same bug that Davis did. So this was a nice proof of concept that this approach can work. But of course, we haven't found anything new yet. I'm waiting for the counts to increase a bit. Like now we have 3. The stability is low because there was a bug that just got fixed yesterday, I think. And also that list of Windows API calls was probably not enough to cover every possible path when things can go funny. So a few words about handling large inputs. Large inputs are not ideal for fuzzing in general because of performance reasons, and they generally increase the state stored in the process. Some of the I/O issues may be solved by mocking, like how the Windows API works when it comes to device access, for example, logging to a console. But when I try to mock all the file operations of Windows, well, I wouldn't recommend. Yeah, but what works are RAM disks. So if you use a RAM disk driver that keeps everything that you need in memory, you can actually read files from the disk. But it's actually the RAM, because we are doing full system fuzzing here. All these like additional elements that you put into the operating system just work. One other thing to highlight is that you really have to be careful with swapping. So when memory contents are written down to disk, because you think it's in memory, but in fact it's not anymore, and this can cause surprises. But I linked an article that deals with this very problem. So can we adapt this technique that we saw here to other parsers in the same product? Yes, we can. For this, I approached the problem basically the dumbest way I could imagine. So to make this whole concept easy and fully automatable. I wrote an extension for Ghidra that basically calculates the cyclomatic complexity of every function in a binary and builds a tree of these functions and associates the value of the sum of the reachable functions with every node. So here we can, for example, see that this is a virtual function table where this particular one has a much larger cyclomatic complexity, cumulative cyclomatic complexity than all the other ones. So that would be a nice target for our fuzzing. This combined with the RTTI information, which is fortunately present in these files, we can really easily select these parts. So our new target became the 7-zip decomposer. I also could verify that we are targeting the right thing because the magic number matching and all the very obvious code was easily identifiable based on this, which is a good thing because the whole binary is like a statically linked mess of everything. Like it has ONRAR, it has zlib, it has all that stuff. If you have bugs in there, then you can use against Symantec. That's another talk. Now we are targeting something custom. So at this point, I still was in like a testing stage. I just wanted to tell whether KFX and AFL around it, or AFL++, can survive its own fuzzing. So I just created one single small 7-zip file from the command line with basic commands. I used AFL++, used Intel PT. That was probably the most advanced thing at this point. I used a single core because that's just testing, and I let it run when I went to sleep. So this is how the harnessing looked like. I'm now placing a breakpoint to that like large complexity function, and another breakpoint right after that function. That will be the harness setup breakpoint. Initiate a scan inside the VM. And at this point, we will see that our first or 0th breakpoint hits. I put a breakpoint to the caller. That will be our stop breakpoint. So I want to see everything that this one function does in this case. I place our usual breakpoints for Windows APIs, and I'm searching memory for the contents of the file I just scanned. Of course, it is known by me, so I can do an easy scan. And there are a bunch of addresses. It looks like that the file contents are already scattered all around memory. Question is, which one is the one that will be actually parsed by our target routine? I just save these addresses. and set up the snapshot. Now we go forward on a single thread. And the snapshot is created. Now, what do we do with those addresses? Of course, I had to implement some crazy machine learning outlier detection. What this code basically does is to run KFX in itself, injecting at the different points that are possible, and we see how long the output of AFL is. It takes a while. The video is edited for brevity, but you will see in a short while that almost all addresses are like this 594, except this one, which reached 642 output lines, which kind of correlates with the number of instructions executed. With this, we can start up AFL++, and our paths are going up, up, up. So this was the point when I went to bed. Yeah, stability is shit. Sorry about that. But after a while, here, 9 hours, we have 22 unique crashes, which is not bad, but are they real? Are they exploitable? What's going on? Turns out that these 22 unique crashes come back to a single heap overflow that is caught at different times of execution, because sometimes the free check the heap structure, sometimes during malloc, so it's not predictable. I couldn't find a CVE for this, but it is an NDA now, so it's dead, not present in the most recent versions. I did a really quick analysis with Riven, which is also a virtualization-based tool to analyze targets like this. And with the free version, you can target 32-bit applications. So pretty good. Here we see the page fault. Like, yeah, that was it. And the page fault was triggered by an out-of-bounds or out-of-page write. If we get back to the source of the D word that was written to it, we find a loop. You can see the loop because the same code is repeating, because it's not a disassembly, it's timeline of the execution. And this loop basically fills up the D word byte by byte. And if we take a look at where these bytes come from, then we will easily recognize our input file. So it's, at least the content is completely controlled. The size is more tricky, but I haven't even investigated this too much because it's already a dead bug, but it's not a totally useless bug, I would say. This is the file contents, yeah. So, unfortunately, when I try to do similar stuff with more modern versions of Symantec, I wasn't this lucky. So bugs didn't just spill out of nowhere. But fortunately, KFX follows the Unix philosophy, kind of. So it does one thing, and it does that well. It harnesses well. Also, with AFL, we got this shared memory map-based inter-process communication protocol, which kind of became a standard among fuzzers. So integrating KFX with libAFL, that allows to, for example, create more informed input generators that, for example, know about the target file format, was similarly easy. I had to submit a like 10-line patch that allowed us to specify what kind of signal libAFL should send to KFX, so KFX can properly shut down the virtual machines. That was it. This is how it looks like. There's no demo because it's so simple. A limitation that we still have, but we're working on it, is that it still passes input files on the host disk. So it's not that efficient that it could be, but the basic interfaces are there, so you can do whatever. With this talk, I kind of want you to, or encourage you to take a look at antiviruses, because I think this is an under-researched area. There are many interesting components in these products, like kernel components. There are memory scanners, there are network scanners, but there can be other good targets for this kind of full system fuzzing. Paranoid kind of software seem like an ideal target, like games and anti-cheat engines, but I'm really looking forward to have some conversations with you about your ideas. And also, the good guys at Mozilla published a blog post recently about how full system fuzzing, which KFX does, can be used to find sandbox escape. So if you're a browser guy, you're in a better position because you usually have source code and all that shit. And also you have this tool available, easy to set up. I also wrote a blog post about how I tried to harness Firefox. I didn't manage to harness, but the message format was in the way, and I only spent like a weekend on it. But if your game is Firefox, you definitely can do things with it. Actually, the guys at the Nix Fuzzer already had their prototype submitted to Mozilla for them to use in order to find IPC bugs, which is great. So in summary, my main point is that virtual machine introspection-based analysis tools are like game changers for offensive research. We can touch parts of applications which you wouldn't even touch with a 10-foot pole otherwise, because it was so nasty and hard to reach, and other hurdles were in the way. With this tool, everything is just a process that you can do whatever with. So, and in particular, KFX is an easy-to-use tool that implements virtual VM-based introspection capabilities that is really easy to integrate to your tools. So, Tamas, please come join me. This was our talk.
Thank you, everyone. Thanks, Bálint.
Yeah, the tool is there, so take a picture if you want to start playing with it tonight. This is us on Twitter, and we'll be around for questions in the close proximity of the beer stations.
Beer station.
Thank you.
Thanks, everyone.